All right, everyone. For the next talk, we have David, who will be telling us about streaming algorithm for Euclidean K-mean and K-median in literal log-in space.
Okay, yeah, thanks to the organizers for inviting me, and thanks for coming. This is going to work with Vincent Cohen-Addad and Samson Zhou, who's here. Okay, so what is the problem we're going to consider? We're going to look at Euclidean K clustering. So we have our input points x1 through xn. We're going to assume that they're each on a grid in d dimensions. So the coordinates are integers from 1 to delta. Distance xy is Euclidean distance. And we're going to be looking at the KZ clustering problem. In this problem, we want to find a set C of at most K centers to minimize the cost of XC, which will just be the sum of Z powers of Euclidean distances of points to their nearest center. Okay. And in this talk, how do I? What is it? Oh, right.
Okay. So the goal, as you stated, seems trivial because you are not asking for any guarantee of the clustering.
Yeah, so I want to get a good approximation. So yeah, well, I'm going to say what this set of K centers is. So we're going to see the points in x1 at a time. We'll look at two models, insertion only. I just see new points. And the other model is I can delete previously seen points. And I want to output a set of K centers and the cost. And I want a good approximation to that objective that I put on the previous slide. We'd like to cluster a stream of n points using, and this is the main point, little o of log n words of space. Okay, so a word is going to be log n delta bits. For convenience, think of delta, the precision of each coordinate, as poly n. So each word is order log n bits. And all previous algorithms used at least log n words of memory. Okay, so at least log squared n bits of memory. We'd like to beat that bound. Okay, so here's our first result. There's a one-pass algorithm on insertion-only streams that outputs a 1 plus epsilon approximation for KZ clustering, in fact, at all times during the stream. And it uses a space bound, which is poly log and delta bits, okay, times dk over epsilon squared, min of k over 1 over epsilon to the z. This term in front is the same as recent best offline core set constructions. And so the main improvement here is previous streaming algorithms had a poly log n dependency, and we're getting a poly log dependence. And we have some lower bounds, though they're not completely satisfactory, but they essentially show that this is not possible in one-pass insertion deletion streams. Okay, if you have questions about that, happy to answer. And so for insertion deletion strings, we instead look at two-pass algorithms. And for two-pass algorithms, we can get a similar dependence on log and delta. So both for K-median and K-means, and in fact, for KZ clustering for any z between 1 and 2, we get polynomial and log words of space. Okay, and polynomial dk and 1 over epsilon. Okay, any question about the results? Okay. So an important concept that we'll use is a core set. So you've seen this many times in the workshop. So a core set is a subset x prime of representative points of x for some clustering objective that roughly preserves the cost. Okay, so for any set C of K centers, if I use my core set points x prime, my cost is roughly the same as using the original data set x. So you can imagine sampling from a certain distribution some input points to form your core set x prime. So here is the formal definition we'll use. And so we say a set X prime with the weight function W is a 1 plus epsilon approximate core set if for all queries C of at most k centers. We have that the weighted cost of X prime using C is within 1 plus epsilon of the actual cost of using C for the original data set. The weighted cost is, I just have a weight function for each of my points in X prime. You can kind of see this is necessary because you're reducing endpoints down to something small. And so this is the weighted cost here. Okay. Yeah, so as I said, offline, there are nice core set constructions. So a result of Vincent, Casper Larson, David Salpic, and Chris Striegelsson is here, shows that you can find a core set with k over epsilon squared times the min of k and 1 over epsilon to the z weighted points. And the nice thing is that this is independent of n. So really the n is just arising from the streaming setting, trying to solve the problem in the streaming setting. And what's one natural way of using offline core sets to solve the problem in the streaming setting? Well, a natural way is to use the merge and reduce framework that Samson talked about yesterday. So suppose there exists a 1 plus epsilon core set construction for KZ clustering using some number of weighted input points. We saw k squared over epsilon squared is always possible. Then we can partition the stream into blocks of this number of points, and we can reduce the blocks and merge them up a tree. So let me show you the picture here. So at the bottom of this picture, we have the stream partitioned into blocks. We take a block and we compute a core set using an offline algorithm. We take the next block, we compute a core set, and we merge the core sets up a tree. Okay, so we're going to have log n levels. N is the length of the stream, log n levels, and in each level we're maintaining a core set. Now, one issue with the merge and reduce framework is that the accuracy epsilon gets worse when you do a merge step, when you go up the tree. And so the typical way of fixing this is to replace epsilon with epsilon over log n. Right? The height of the tree is log n. And by doing that, well, as we said, there are log n levels. You're getting a 1 plus epsilon over log n approximation at each level. And so raising 1 plus epsilon over log n to log n, you get a 1 plus over epsilon approximation, which is great. But the issue is you're going to incur additional log factors now, because what you're doing is you're replacing this epsilon with epsilon over log n. So in your blocks, the size of the block of the stream is going to be this function f of k and log n over epsilon. And I mentioned a good offline core set construction earlier that had a 1 over epsilon squared dependence. And so given this extra log n here, it's going to turn into a log squared n in your space. And you also have log n levels in this tree. So for k-means clustering, for example, this would give k squared over epsilon squared log cubed n points. Okay, so this is, you can see where the log factors are coming from now in the streaming set. Both from epsilon and both from the height of the tree. Okay. And yeah, the question we asked is, do there exist streaming algorithms that use many fewer than log n words of space? And there's a long line of work on clustering in the streaming model. So work of Harp-led, Mazumder, Harp-led, Kushal, Chen, Feldman, Langberg, Bregman et al., Cohen-Addad et al. If you look at all these works, there is at least a log n dependence in the number of words of memory. And our first result is we show that we can, in fact, get a polylog log n dependency. Okay, so how are we going? Yeah, any questions? Good. All right. How are we going to do this? So the idea is we're going to combine sampling. By the way, this is all for insertion only strings so far. The idea is we're going to combine sampling with the merge and reduce string. Okay, so sampling is going to effectively reduce the stream size that we feed into our merge and reduce algorithm. Okay, so let me say how this works. So yeah, what is a good sampling scheme for core set constructions? Well, a simple way to find your core set X prime is to uniformly sample points of your data set X into X prime. But you know, this is not good if we have an outlier. So there's some outlier here. You'll need many samples in order to find a good representative set of points. So a better way is to use importance sampling. So we sample each point X in our input. But by the way, this is just offline for the moment, not streaming. We sample each point X in our input into our core set X prime with probability proportional to its cost. Okay, so this point is far away from these cluster centers and it has a high cost. Okay, so its distance to its nearest center is large. It has a large probability of being sampled. Now that makes sense if I fix a particular set C of clusters. You know, in that particular case, you can show that importance sampling only needs 1/epsilon² samples, and you can approximate the cost to that particular set of centers. But it's not great if I change my set of centers, right? If I have
that per cluster or for all clusters?
Yeah, that was just for one cluster. Okay, so that's the issue. So this is for I can preserve the cost for one particular clustering with 1/epsilon² samples. But yeah, if you look at a different set of cluster centers, maybe this is no longer an outlier because there's a cluster center over here, but maybe some points over here are outliers. And so the probability is that I sample them should be different. And so we need to handle all possible sets of K centers in our sampling procedure. And this motivates the definition of a sensitivity that has been discussed in this workshop. So we sample each point X with probability, which is the maximum over or supremum over set C of K clusters of the cost that X contributes in the clustering using C over the total cost. Okay, so this maximum captures the fact that I can change my clustering and I need to be good for any possible clustering. Now, again, this 1/epsilon² number of samples just means that I'm a good, I'm good for one particular, it doesn't give me a high probability bound. So what I can do is now I can, take more samples and do a union bound over a net of all possible sets of K centers. Okay, and these sampling probabilities, since they're the supremum, will be good for any set of K centers. Okay, and the net, is large, but the number of samples is logarithmic in the net size. Okay, so yeah, this is the sensitivity. This S of X, this supremum, and the total sensitivity is just the sum of the sensitivities. And if for each data point you're deciding whether or not to include it in your core set, then the expected number, with probability proportional to its sensitivity, or just its sensitivity, the expected number of points to include is the sum of the sensitivities. Okay, so it's important that this sum be small. And then you have to multiply that sum by some log of a net size to do the union bound, but that is a small factor for us. Okay, well, in a data stream, we don't have the sensitivities because we haven't seen all of them. So we define the notion of an online sensitivity, right? So we don't have this sensitivity. Instead, we're going to look at an online sensitivity of a point xt. Xt is the t point we see in the stream. And the online sensitivity, I'll call 5xt, is the max over clustering sets of size sets of at most K centers of the cost of xt to C over the cost of the entire prefix of the stream, including xt to C. Okay, so it measures the importance of the current point x so far in the stream. Okay, so this is an important notion. This notion we can actually compute in a stream. Yeah, I guess one question is the sum of these online sensitivities still small? Because that's going to influence the number of points we sample in the stream.
How much memory do you need to compute that?
Yeah, it's another question is how do we compute the online sensitivities, right? So both time and space. So yeah, let's see how we're going to do that. So the streaming algorithm is we want to sample each point xt with this probability. It's proportional to the online sensitivity, times something for the union bound over a net, the min of 1 and that. So yeah, how to compute or approximate this? So the idea is we're actually going to use a core set itself to approximate the online sensitivity. Okay, so we use this 1 plus epsilon core set that we're going to be maintaining inductively to inductively approximate the next sensitivity, online sensitivity. Okay, so we use the samples obtained from our online sensitivity sampling at each time t minus 1 to obtain our core set, and therefore our 1 plus epsilon approximate core set, and therefore to give a good approximation of the next online sensitivity. And so by induction, this will hold at all times in the stream. Okay, so it suffices to have a core set to estimate the online sensitivities. And this is not great as a streaming algorithm by itself either. Why? Because, well, you can show that the sum of the online sensitivities is going to have a polylog n delta in it. That's something that we don't want. And so how are we going to get around that? Well, the idea is that these sample points that we see in the actual stream, we can view them as forming a new stream, x prime. Okay, so you have this actual original stream, you're sampling from it and creating a new stream, x prime. And the point is that this new stream, x prime, has much smaller length than the original stream, right? The length is going to be roughly the number of sensitivity samples. And so the length is going to depend polylogarithmically on the original length. Okay, so now what can we do with this new stream x prime? Well, okay, just think about that. But as an aside, why are the sum of the online sensitivities? Why is the sum of online sensitivities small? Well, yeah, let's try to get a handle of the online sensitivities. Here's one. If you had k plus 1 points, and these were all cluster centers, then this 1 point here would have sensitivity 1, right? All these costs would be 0, and you'd have 1 divided by 1. And you can move your clustering around anywhere. And so, if I have k plus 1 distinct points, the sum of the sensitivities can be at least k plus 1. What about the online sensitivities? So we have an argument showing that the sum of the online sensitivities is not too large. Okay, so it's not too much larger than k. It's k times log squared nd delta. We don't know if this is tight. Maybe it's possible to get k times log nd delta. It turns out that it doesn't actually matter for our application if that log factor is tight or not. I'm not really going to say how we get this bound, but roughly in the offline setting, the sum of sensitivities can be shown to be order k. And in the online setting, you can partition the stream into places where the clustering cost doubles. And then by relating sensitivities to another quantity, you lose another log factor. Roughly combining these steps, you get k log squared. I'm happy to talk more about that offline. But so that's what the sum of the online sensitivities is. And here is the algorithm using them. So we're going to perform online sensitivity sampling to implicitly create this new stream x prime. It's going to have polylogarithmic number of points in N, but we're actually not going to store this new stream X prime. We're instead going to feed this stream X prime into a merge and reduce algorithm. Okay, so this merge and reduce algorithm, it's inductively maintaining this core set for us. So it's enabling us to predict the next online sensitivity. And we see a new point in the actual original stream, and we decide to include it or not with probability proportional to that sensitivity. And so we see this substream of samples from the original stream, that's X prime. And this X prime is what merge and reduce is being run on.
Maybe.
Yeah.
So you said before we mentioned the merge and reduce and explain it like the space there is or something like log n.
Right.
So my question, like in this current context, what you get from step one is like a shorter step of log n but with weights.
Yeah.
So the key question is like in step number 2, even the merge and reduce will depend on the total weight, which is about
It doesn't
10,
depend on the total weight.
or the number of distinct points, which is like log n.
That's exactly the point. It only depends on the number of distinct points because you can store the batch of distinct points and then
You like
reduce
half it, but you feel like a 3.
That's right. Yeah. So it depends on the number of distinct points, and that's why this. So that's exactly the point. So let me say what Rovi said. This new stream X prime, it has length, some poly KD over epsilon times polylog n delta. This is the number of distinct points in the stream. We can store, we can do the merge and reduce on the set of distinct points because we store a batch of distinct points and then we reduce them with this core set. Okay, so we run a merge and reduce framework on X prime. And the total space used by merge and reduce was this function of k and the accuracy, which was epsilon over log n, and we had log n levels in the tree. N was the length of the stream, the number of distinct points we saw. And by feeding in the samples from online sensitivity sampling, we replaced the stream with a length which is much shorter. Okay, so the length of the stream now is only polylog n delta. And this replaces the log n delta with log n delta. And that's roughly the idea of the whole insertion only algorithm.
So,
Yeah.
so when the merge and reduce is no longer a streaming thing, so you can't apply this again.
You can apply this again. Now we're actually going to have the issue is with the weights. Like if you try to apply it again, you don't get anything additional to that. Yeah. But it's a good open question. Like we don't know if we can get rid of log completely. So yeah, it's a nice question. Okay, so yeah, that's our results for insertion only streams. Yeah, I don't have so much time, but let me say a little bit about insertion deletion streams. The idea is we're going to try to use the first pass. As I said, these are 2-pass algorithms to estimate the sensitivity of each point in the stream, and we use the second pass to perform the sensitivity sampling. Okay, so yeah, let me try to give you a rough idea how this works with very limited time. So okay, let me skip this slide. The idea roughly is there is an existing 1-pass insertion deletion algorithm that can give you a reasonable approximation, a reasonable approximate clustering. Okay, so it can give you a log k plus log delta approximate clustering. This is using an EMD sketch of Backers et al. And it uses a reasonable amount of space. Okay, so if you've seen techniques like pyramid embedding and L1 sketching, this is what it's based on. It uses a fairly clever argument using doubling dimension arguments of k-sparse vectors. So it uses nice net arguments to improve what would naively be a log delta approximation. So we get some approximation using this sketch. We can compute this sketch in the first pass. And using this sketch at the end of the first pass, we can use it as a data structure that can allow us to estimate the sensitivity of any point. Now, the approximation guarantee that I set here in the first pass is very important because it translates into the amount that we have to oversample by when we sample by sensitivities in the second pass. Okay, so it's important that it's not a log delta. It's important that it's probably log delta. And so in the second pass, what we do is we sample according to sensitivities, and that itself is a little bit problematic because when you sample a point that could be deleted, well, how do you deal with that in a stream? So for each point you see in the stream, you still sample it with probability proportional to its sensitivity, but you feed it into a substream, and this substream you prime. It might have a lot of points at intermediate stages in the stream, but at the end it's promised to have a small number of points. Okay, because what you're doing is you're taking the total number of sensitivity samples that you would have even if you have deletions. Okay, so the idea is, first pass, compute this sketch to give you this crude approximation. Use that as a tool to estimate sensitivities in the second pass. In the second pass, each time you see a point, you just sample it proportional to its sensitivity, and you feed all those samples into what's called a sparse recovery data structure. And the point of this sparse recovery data structure is at the end of the stream, if you're promised you have a small number of non-zero coordinates, which you will, a number of non-zero points, which you will because the sum of the sensitivities is small, then you can recover all the points that you sampled. Okay, so yeah, I mean, the short story is, get a crude approximation using this existing EMD sketch, do sensitivity sampling in the second pass, but you have to deal with the fact that you have deletions, so you feed your samples into a sparse recovery sketch, which is guaranteed to recover all of the points that were sampled and not deleted at the end of the stream. That's the rough idea for K-median, and that's the whole algorithm here. Question?
The crude approximation, does it know the number of points in every cluster?
Yeah, so you can actually get, so this EMD sketch, it actually gives you an approximate number of points in all the clusters, which you need for the sensitivity calculations, and let me just mention one cool thing about KZ clustering, or maybe two cool things. I don't really have time to get into them at all, but one idea behind that K-median sketch that we're using from previous work is a quad tree embedding, which many of you have worked on. So you have a set of points, and you take a grid decomposition, a randomly shifted grid decomposition, recursive and log delta levels, and you snap points to their grid location, and this works great for K-median. So then you can compute the L1 norm of the number of points in each cell. This is how the previous work works. But let me just tell you one thing is that this quad tree embedding is very horrible for K-means, because if you, in this randomly shifted quad tree, if you cut off a center that's very close to a set of points, then since you're squaring the distance, it can increase the cost by a lot. So the rough idea, the fix that we do is let me just show you the picture. When we're making a query, if it's too close to a grid cell, then we reflect the query into the neighboring grid cell. Okay, and this prevents this this bad thing of happening of cutting points to a nearby cluster and causing the distance to increase too much. We carefully set the parameter at which we decide to reflect our point. And this is how we handle K-means.
What if you're close to a corner?
So
you have at least two cells there.
Yeah, so we would do this for all the side lengths. Yeah,
Okay.
we can still show that an expectation that you'll have order K centers. But so this is the idea here, and this is a cool idea, and this idea is also not enough to get our final bound, because if you work it out, you'll see that you get for K-means Z is 2, you'll get a log delta approximation by doing this. And if you remember what I was saying, that this approximation translates into how much you need to oversample by sensitivities, that log delta will get pushed into the space, which we don't want. So we have one other idea to fix this, which is that, yes, you can try to do that. Let me just skip these slides. The last idea is, well, we don't actually have to store the sample points explicitly. Instead, what we do is for each sample point, we're going to store its offset from a near optimal solution. Okay, so we're going to find a near optimal solution, and instead of storing the point, which would be log delta bits, we're going to store the center that serves it, and we're going to look at the difference of the center that serves it and that point, and we're going to round each of the coordinates to some precision. And we can show that this still works because you can charge the rounding error to the near optimal solution. Okay, so we need to do this like the k-mean solution. We actually need to store log delta points, which is what we don't want. But the way we're able to get small space is we don't need to store those points with high precision. We can round them. So that's an extra trick that we do here. So yeah, sorry that was kind of fast, but I wanted to just say the main ideas here. To summarize, we get this insertion only algorithm, which had poly log log n words of space. It was one pass. That's not possible with two passes. That's not possible with deletions in one pass. So we look at two passes, and for k median and k means, we're able to get poly log log dependence in the space. And that's all. Thanks.
Any quick question for David?
Yeah.
If you have random order streams, could you do better?
Oh, that's a good question. You mean with just insertions?
Yeah. I don't know what a random order.
Or a deletion would even mean, right? Yeah.
I mean, because you can actually get a constant factor, I think, without any dependencies on delta or n.
I mean, like use a prefix to get some kind of constant factor approximation.
So the total sensitivity is gonna pay a log? If it's
I think you would still pay a log for the it might be easier to analyze, but I think you would still pay a log just because the cost can, can change log times, even if it's in a random order. Yeah. So I don't know if it gives better balance.
And so, like, by the same token, we could get something better if you only wanted a constant factor rather than a Horset.
You
I
mean
mean, like in
you only want a solution rather than
yeah, it's just
I mean, we kind of need the core set at each time step to estimate the next online sensitivity.
Yeah.
So I think since we're paying for that amount anyway, I don't think our algorithm would do any better.
Yeah.
Yeah.
no, like with your algorithm, I think it's clear you
Oh, is there some other algorithm?
Yeah, just but like hypothetically, if any of those techniques could without going through the Horset thing.
Yeah, I don't know. It's a good question. Yeah.
All right, let's thank David.